Good day, class. You're welcome to our chemistry class. And in chemistry today, we shall be looking at the topic, the mole. So what exactly is the mole? One mole of a substance is the amount containing as many elementary entities, which are the Avogadro number of particles. Now, the particles that are involved are several. It may be atom, it may be an atom, it may be a molecule, it may be an ion, it may be protons, electrons. All these particles, the amount containing as many of these elementary entities is known as the mole. And all these are referred to as the Avogadro's particles. The Avogadro's number is taken as 6.02 times 10 to the power of 23 particle, in which the particle could be an atom, it could be a molecule, it could be an ion, proton, and the rest. And then that leads us to the mole concept. The mole concept is about how mole is expressed. We shall look at four headings with which we express the mole. The first one is mole in terms of the formula. The second is mole in terms of relative molecular mass. The third is the mole in terms of the Avogadro's number. And the fourth one is the mole in terms of the molar volume. Alright, so we shall take mole in terms of formula. Now, when it has to do with mole in terms of formula, we use the formula which is number of moles of a substance equal to the mass of the element divided by the relative atomic mass or the relative molecular mass of the element. Alright, so with this we will take the first question. It says calculate the number of moles of atoms present in 20 grams of sodium hydroxide. We have sodium hydroxide. We were given 20 grams of this. So that is the mass of the element. This is a compound that has a molecular mass. So the molecular mass of sodium hydroxide will be sodium has an atomic number of 23, oxygen has 16, and hydrogen has 1. When we add all this, we have 40 grams. Hence, number of moles of sodium hydroxide will be 20 over 40, and so we have 1 over 2. That is 0.5 mole. Hence, this is the number of moles of atoms present in 20 grams. Now, here is the second question, which says determine the number of grams of substance present in 0.25 mole of calcium trioxocarbonate 4. Alright, so in this question, we have calcium trioxocarbonate 4, and we're given 0.25 mole of it. We have to find the mass present in 0.25 mole. So first is to find the relative molecular mass of calcium trioxocarbonate 4. Calcium is 40, carbon is 12, oxygen is 16, multiplied by 3 because we have 3 atoms of oxygen present there. And so when we add all this, it gives us 100 grams. Hence, using this formula, we are looking for the mass of the element. So we have it that mass of the element equal to mole times relative atomic mass, relative molecular mass. So that's 0.25 multiplied by 100, and that produces 25 grams. And so we have it that we have 25 grams in 0.25 mole of calcium trioxocarbonate 4. So next, we want to calculate mole in terms of the relative atomic mass or relative molecular mass. Relative atomic mass is basically the mass of an element, while the relative molecular mass is the mass of a substance or a compound. So for instance, if you have that 1 mole of sodium, the relative atomic mass of sodium is 23 grams. Hence, this is the mass of 1 mole of sodium. If you have 1 mole of oxygen gas, this is a molecule of oxygen. 1 mole of oxygen equal to 16 times 2, and that is 32 grams. So 1 mole of oxygen gas is 32 grams. You could also have ion, like 1 mole of chlorine ion is 35.5 grams. You could have a compound like 1 mole of H2SO4. There's 1 in front of it, so it is about calculating individual atomic mass. So we have 1 times 2 plus sulfur is 32 grams plus 4 times 16. That's 4 times oxygen has 16 grams. and the 4 applies only to oxygen. And so when we add all this produces 98 grams. So all these are relative atomic mass. This is the relative molecular mass of tetraoxosulfate 6 acid. So let's take some questions in this line. The first question says that we should calculate the number of moles present in 11 grams of carbon 4 oxide gas. So we have carbon 4 oxide gas. Let's derive the relative molecular mass of this. Carbon has an atomic mass of 12. Oxygen has 16 multiplied by 2. Right, so we have 12 plus 32, and that is 44 grams. Now all these are per mole. So we are asked to calculate number of moles present in 11 grams. This is the relative molecular mass. So we are saying that 1 mole of CO2 contains 44 grams. That is the standard. But how many moles of CO2 are we going to have in 11 grams? So when we cross multiply, 1 multiplies 11 and x multiplies 44. So we are left with x equal to 11 over 44. And we have 0.25 mole of carbon 4 oxide gas. So that is the answer. Here is the next one, which says that we should determine the number of grams of substance present in 0.1 mole of sodium trioxocarbonate 4. Right, so in this question, we have Na2CO3. We are to calculate the number of grams present in it. Yes, we have to calculate the relative molecular mass of this compound. So here we have sodium as 23 multiplied by 2 plus our carbon is 12, then oxygen is 16 multiplied by 3. This is 46 plus 12 plus 48, and that gives a total of 106 grams per mole. So here is the relative molecular mass of Na2CO3. So from here, if 1 mole produces 106 grams per mole, now from the question, what will 0.1 mole contain? So 0.1 mole will contain x. For us to get the x, we'll multiply x by x times 1. So x equal to 0.1 multiplied by 106. And that will produce 10.6 grams. So that is the number of grams of Na2CO3 present in 0.1 mole of sodium trioxocarbonate 4. The third part is that mole can be expressed in terms of the Avogadro's number of particles, and we said the particles could be atoms, molecules, and the rest. Now what we are saying now is that 1 mole of calcium, for instance, will contain 6.02 times 10 to the power of 23 atoms. If you have an ion, for instance, 1 mole of sodium ion will contain 6.02 times 10 to the power of 23 protons. Alright, so if you have 1 mole of Cl minus, that's chlorine, will contain 6.02 times 10 raised to the power 23 electrons. So it depends on the substance we are talking about. If it's a proton, we have protons, or molecules, we have molecules. For instance, HCl, 1 mole of HCl will contain 6.02 times 10 raised to the power 23 molecules. So with this, we can solve some questions. We have that calculate the number of ions present in 2 moles of potassium ion. So here, potassium ion, that is a proton. We are aware that 1 mole of potassium ion equals to 6.02 times 10 raised to the power 23 protons. Therefore, 2 moles of calcium ion will be 2 multiplied by 6.02 times 10 to the power 23, and that will give 12.04 times 10 raised to the power 23 protons. It's as simple as this. Another question says calculate the mass of substance present in 24.08 times 10 to the power of 23 molecules of tetraoxosulfate 4 acid. So in this question, we have that 1 mole of H2SO4 will contain 6.02 times 10 to the power of 23 molecules, and this is still equal to calculating the relative molecular mass of H2SO4. When we calculate it, we have 98 grams. So 1 mole of H2SO4 is 98 grams, and it's also equal to 6.02 times 10 raised to the power 23. Now we're told to find the number of grams present in 24.08 times 10 raised to the power 23. So what we'll do is that we'll equate this with this. So if you have 98 grams of H2SO4 to be equal to 6.02 times 10 to the power of 23 molecules, how many grams of H2SO4 are we going to have in 24.08 times 10 to the power of 23 molecules? We'll cross multiply, that is x multiplies this. That's 6.02 times 10 to the power of 23 times x equal to 98 times 24.08 times 10 to the power 23. So we have that x equal to 98 times 24.08 times 10 to the power 23 over 6.02 times 10 to the power of 23. And so when we solve all this, we'll have 392 grams of H2SO4 present in it. Alright, so still on the Avogadro's number, we are to determine the number of particles in 1.2 gram of magnesium metal. Here we have that 1 mole of magnesium is 24 grams and is also equal to 6.02 times 10 to the power of 23 atoms. Now we are asked the number of particles in 1.2 grams. So in 24 grams, we have 6.02 times 10 to the power 23 atoms. How many atoms do we have in 1.2 grams? When we cross multiply, we have 24 times x equal to 1.2 times 6.02 times 10 to the power 23. And so we have x equal to 1.2 times 6.02 times 10 to the power 23 over 24. And so when we multiply all this out, we can have 1.2 times 6.02 over 24, then multiply by 10 to the power 23. So when you multiply all this with the calculator, you have 0.3010 times 10 to the power 23 atoms, or you have it in particles. Alright, so next is to express the mole in terms of molar volume. Now it's important to know that the molar volume of a gas is defined as the volume occupied by 1 mole of the gas at standard temperature and pressure. And the value of the molar volume of all gases at that standard temperature and pressure is 22.4 dm cubed, or 22,400 cm cubed at standard temperature and pressure. Alright, so after that is noted. So if you have a gas such as oxygen gas, 1 mole of oxygen gas contains 22.4 dm cubed at STP. 1 mole of chlorine gas contains 22.4 dm cubed at STP. Even a compound, 1 mole of CO2 gas contains 22.4 dm cubed at STP. So with this, we shall solve some questions. Alright, so here comes the next question, which says calculate the volume occupied by 3 moles of carbon 4 oxide gas at standard temperature and pressure. So we have that 1 mole of CO2 gas equal to 22.4 dm cubed. And so if you have 3 moles of CO2, what will be the volume? That will be 22.4 times 3, and that will give 67.2 dm cubed at standard temperature and pressure. Here's the next question, which says that how many grams of gas are present in 5,600 cm cubed of chlorine gas at standard temperature and pressure? Here we have that 1 mole of chlorine gas equal to 22.4 dm cubed, which is same thing as 22,400 cm cubed. And that 22,400 cm cubed is equal to chlorine, which is 35.5. So one atom of chlorine is 35.5, but here we have 2, so we multiply by 2, and that will be 71 grams of chlorine, which gives 22,400 cm cubed. So 5,600 cm cubed will contain how many grams? So we have x equal to 71 times 5,600 over 22,400, and that will give 17.75 grams of chlorine gas. So next we look at the application of the mole concepts. The mole concept is applied when we are calculating mass, volume of gases and liquids. From what we've discussed before, we know now that 1 mole of a substance is equal to the relative atomic mass or the relative molecular mass of that substance, and is also equal to the Avogadro's number, and it is also equal to the molar volume of that particular substance at standard temperature and pressure. And so this relationship is what we are going to use when we are talking about application of the mole concept, and we'll be looking at it under 4 headings, which are mass calculation, mass volume calculation, gas volume calculations, then mass liquid volume calculations. So let us look at the details of all this. Here, this question says calculate the mass of calcium oxide formed when 1.5 gram of calcium is completely bound in oxygen. For us to solve this question, we need to first put down the equation of this reaction. We have calcium bonds in oxygen to produce calcium oxide, and so we need to balance the equation. We have 2 over here, so if we put 2 here and we put 2 here, we have a balanced equation. Here we have a solid, we have a gas, and we have a solid. So from here, the mass that we will be considering are the mass of calcium oxide and that of calcium, because we're told that we should calculate that of calcium oxide, and then we're given that of calcium. Now this is what I mean. First, what is the relative atomic mass of calcium? 1 mole, so we have 2 mole of calcium here, we have 1 mole of oxygen, and we have 2 moles. Then 1 mole of calcium gives us 40 grams. Hence 2 moles will be 80 grams. And for calcium oxide, we need to calculate the relative molecular mass. Calcium is 40 and oxygen is 16. So when we add this, we have 56 grams. Now when we're talking about 2 moles of calcium oxide, and that will yield 112 grams. So 112 grams of calcium oxide was the yield in this reaction. And so what will be the yield when 1.5 gram of calcium was used? What will be the calcium oxide mass that will be produced when 1.5 gram of calcium is used? And so what we will do is we cross multiply it. We have 80 multiplies x, which is 80x, and then 112 times 1.5. So we have x equal to 112 times 1.5 over 80, and that gives us 2.1 gram of, and so that's 2.1 gram of calcium oxide. This is what is produced when 1.5 gram of calcium is used. Alright, so we have the next question here, which says that we should calculate the mass of sodium tetraoxo sulfate 6 formed when 0.5 mole of sodium hydroxide reacts with tetraoxo sulfate 6 acid. Alright, so having our equation, we have sodium hydroxide reacting with H2SO4, and this produces Na2SO4 plus H2O. So these are the products and these are the reactants. Next is to check if it is balanced. Obviously it's not balanced because we have one atom of sodium here and we have two atoms of sodium here. And so if you have two placed before sodium, sodium is balanced. We have 2 of oxygen here, we have 4 here, we have 4 here, and we have 1 here. So if we have 2 over here, we have 2 of oxygen. Okay, that's 6, and then 6. Then hydrogen, we have 2 hydrogen, then we have 2 hydrogen, making 4. 2 times 2, we have 4. So the equation is balanced. Now, what are the reacting masses in this question? We are concerned about sodium tetraoxosulfate 6, which is this, and sodium hydroxide. Okay, what we'll do now next is to know the reacting moles. We have 2 moles of sodium hydroxide and we have 1 mole of sodium tetraoxosulfate 6. Next, we look for the relative molecular mass of sodium hydroxide. Sodium is 23, oxygen is 16, and hydrogen is 1. When we add this, we have 40 grams. Next, for Na2SO4, sodium is 23 multiplied by 2, sulfur is 32, and oxygen is 16 times 4. When we calculate all this, we have 142 grams. Now, from the question, we have to calculate the mass of Na2SO4 formed when 0.5 mole. From the question, 2 moles of NaOH produces 142 grams of Na2SO4. So we have 2 moles and then we have 1 mole of this. So this is 142 for sodium tetraoxosulfate 6. If we have 0.5 mole of NaOH, how many grams of Na2SO4 are we going to have? So we cross multiply. This multiplies this, so that's 0.5 times 142, and then this multiplies this, that's 2 times x. So x equal to 0.5 times 142 over 2. So the value of x, when we multiply all that, is 35.5 grams. Hence, that is the mass of Na2SO4 produced when 0.5 mole of sodium hydroxide is used. Still working on the mass calculations. We have to calculate the mass of lead-2 tetraoxosulfate 6 formed when 0.01 mole of tetraoxosulfate 6 acid reacts with lead-2 chloride. Alright, so the first thing is to get the equation of the reaction. We're told that tetraoxosulfate 6 acid reacts with lead chloride, and that will produce PbSO4 plus HCl. Next, we'll check to balance our equation. We have 2 atoms of hydrogen here, we have 1 here, so we could place 2 here, and that balances the equation. So 2 hydrogen, SO4, lead and lead. Okay. Now, we're told that we should calculate the mass of lead-2 tetraoxosulfate 6, which is this, formed when 0.01 mole of tetraoxosulfate 6 acid, which is this, and we're given 0.1 mole. Alright, react with that. So we need the mole to the mass. Now we look for the relative molecular mass of PbSO4. Lead has 207 grams, sulfur is 32 plus 4 times 16 of oxygen. When we add all this, it produces 303 grams of PbSO4. So with this information, we will now have it that 1 mole of H2SO4 produces this, which is 303 grams of PbSO4. Hence, if you have 0.1 mole of this, how many grams of PbSO4 will we have? So we cross multiply by having x times 1, which is x, equal to 0.1 times 303, and that yields 3.03 grams of PbSO4. Hence, we'll have 3.03 gram of PbSO4 yield when 0.1 mole of tetraoxosulfate 6 acid is used. We proceed to the mass volume calculations. And so we have questions as such. Calculate the volume of carbon 4 oxide gas at STP when 5 grams of zinc triisocarbonate 4 is heated strongly. Next, we'll get the equation of the reaction. We're told that ZnCO3, that is zinc triisocarbonate 4, was heated strongly, and that will produce zinc oxide plus carbon 4 oxide. Now let's calculate the volume of CO2, which is this, at STP when 5 grams. So we have the mass of this to the volume of this. To solve that, we need to get the relative molecular mass of ZnCO3. Zinc is 65, carbon is 12, then oxygen is 16 times 3. When we add all this, it produces 125 grams of ZnCO3. So with this, we can now relate it that 125 grams of zinc produces 1 mole of CO2, and 1 mole of CO2 is 22.4 dm cubed. So this is, we have 1 mole of this, we have 1 mole of this. If we now have 5 grams of ZnCO2, what is the volume of CO2 that will be produced? So we have it at x equal to, we will cross multiply, 5 multiplies this. So 5 times 22.4 divided by 125 grams. And that gives 0.896 dm cubed of CO2. Take note as standard temperature and pressure. Here we have the next question, which says that to calculate the mass of iron 2 sulfates required to react with dilute hydrochloric acid to produce 112 cubic centimeter of hydrogen sulfide gas at standard temperature and pressure. So first we'll write the equation of this reaction. We're told that hydrochloric acid, that's HCl, reacts with iron 2 sulfide and it produces FeCl2 and hydrogen sulfide. Now we are told to calculate the mass of iron 2 sulfide, which is this. We are dealing with mass required to react with HCl to produce this volume of hydrogen sulfide, and then this, that is volume. So with this, we'll first check to know if our equation is balanced. From here, we have 1 of hydrogen and we have 2 of hydrogen here. So if we place 2 here, we have the equation balanced now. So we have 2 of hydrogen, then 2 of chlorine, 2 of chlorine, 2 of hydrogen. Next, we'll calculate the relative molecular mass of FeS. Iron is 56 and sulfur is 32. And so when we add this, it produces 88 grams. Next, we have 1 mole of this and we have 1 mole of hydrogen sulfide. And so we have that 88 grams of iron sulfide produces 22,400 cm cubed of hydrogen sulfide gas. Hence, how many grams of sulfide is required to produce 112 cm cubed of hydrogen sulfide gas? So when we cross multiply, x multiplies 22,400 and that's equal to 88 times 112. Hence, x equal to 88 times 112 over 22,400. And so when we multiply this, it will produce 0.44 grams of hydrogen sulfide at standard temperature and pressure. Comes another question under mass volume calculations. We have to calculate the volume of hydrogen gas measured at 30 degrees Celsius at 720 mm mercury when 6.5 grams of zinc reacts with hydrogen chloride. Alright, so first thing is to get the equation. We're told that zinc reacts with hydrogen chloride and that produces zinc chloride plus hydrogen gas, hydrogen chloride. Next is to balance this equation. We have 2 chlorine here, we have 2 hydrogen, so we place 2 here, hence the equation is balanced. Now here, we need to get the reacting mass or volume. We have to calculate the volume of hydrogen gas. So volume, and there are some conditions which are 30 degrees Celsius and 720 millimeter mercury when 6.5 gram of zinc. So zinc, which is the mass. So from here, we will relate it that we have 1 mole of zinc and we have 1 mole of hydrogen gas. Zinc has an atomic mass of 65 gram. So 65 gram of zinc produces, alright, so we have 1 mole of hydrogen gas, which is the same thing as 22,400 cm cubed volume. If we have 6.5 gram of zinc, what will be the volume of hydrogen gas that we produced? And so we have X equal to 6.5 times 22,400 over 65. And when we multiply this out, we have 2240. That's 2,240 cm cubed of hydrogen. And so with this information, that is what we'll have at standard temperature and pressure. But the question says that we should calculate the volume at 30 degrees Celsius and at 760 millimeter mercury. That's for pressure. This will take us to our gas equations, most especially the general gas equation, which says that P1 V1 over T1 equal to P2 V2 over T2. Let's take our P1 to be the standard pressure, which is 760 millimeter mercury. Let's take our T1 to be the standard temperature, which is 273 Kelvin. And we take our V1 as the volume which we have here, which is 2,240 centimeter cubed. Then for P2 is the pressure which we are given, that is 720 millimeter mercury. So 720 millimeter mercury. And we take our V2 as what we are looking for. And the T2 we are given to be 30 degrees Celsius, which needs to be changed into Kelvin. That will be 30 plus 273, and that is 303 Kelvin. And so we'll make use of this information to solve this question. Now we are looking for V2, so we can make V2 the subject of this equation. We cross multiply this, bring this here and bring this over here. So we have P2 V2 T1 equal to P1 V1 T2. Hence, V2 equal to P1 V1 T2 over P2 T1. So we will substitute our values into the equation. P1 is 760, V1 is 2240, and our T2 is 303 over P2 is 720 and our T1 is 273. And so when we calculate all this, we'll have 2624.3 cm cubed as the volume of hydrogen gas at 30 degrees Celsius and 720 millimeter mercury. So here is our final answer. Alright, so next we'll look at gas mass, gas volume calculations. Now in this case, we are considering gases, no longer considering solids. And so we have a question such as 40 cm cubed of nitrogen gas reacts with 60 cm cubed of hydrogen gas to form ammonia gas. Calculate the volume of unused and the volume of ammonia formed at the same temperature and pressure. Now let's get the equation of this problem. We're told that nitrogen gas reacts with hydrogen gas to produce ammonia gas. Now all these are gases. We're told that 40 cm cubed of nitrogen gas reacts with 60 cm cubed of hydrogen gas to form ammonia gas. We have to calculate the volume of unused and the volume of ammonia gas formed. Now for us to calculate this, it will take us to Gay-Lussac's law, which tells us that when gases react, they do so in volumes which bear a simple ratio to one another and to the volume of the product. And so that is what we are going to use to solve this. Now, we have 1 mole of nitrogen here. Now, what we'll do next is we need to check if this equation is balanced, because it is not balanced. We have 2 atoms of nitrogen here, and we have 1 atom here. We have 2 hydrogen atoms, we have 3 over here. What if we place 3 over here? That would be 2 times 3 is 6, and we place 2 over here. So we have 6 atoms of hydrogen here, we have 6 atoms of hydrogen here, and we have 2 atoms of nitrogen, and we have 2 atoms of nitrogen here. Hence, the equation is balanced. Next, we need to consider the reacting moles. We have 1 mole of nitrogen, and we have 3 moles of hydrogen gas. We have 2 moles of ammonia gas, which is same thing as 1 volume, 3 volume, and 2 volumes. The next thing for us is this: 1 volume of nitrogen gas, we're given 40 cm cubed, while 3 moles of hydrogen gas were given 60 cm cubed. Now, to get the product volume, we need to consider what would have been 1 mole of all the reacting gases. So if we have 1 mole of each, 1 mole of hydrogen gas here would have been 20 cm cubed, whereas 1 mole of nitrogen gas here was 40 cm cubed. With that, we can now say that for them to react in simple ratio, we are going to adopt the gas that has the lower volume per mole. That is what we are going to adopt. And what does that mean? We are not going to say that since 1 mole of hydrogen gas is 20, this is what we are going to use to determine the number of moles or volume of ammonia that we produce. So from here we have that 40 cm cubed will be produced of ammonia gas. Then when we consider our nitrogen gas, in which we had 40, this is too high. So what we need to do is that we will subtract 20 from 40, because they are reacting in simple ratio to one another. So out of the 40 cm cubed of nitrogen, only 20 cm cubed is going to be used. Hence, the unused gas, which is nitrogen gas, is 40 minus 20, and that is 20 cm cubed. While the volume of ammonia formed will be equal to 40 cm cubed. And so here is how we solve this. We consider this question: 100 cm cubed of carbon 2 oxide gas reacts with 80 cm cubed of oxygen gas. Calculate the volume of the resulting gas and the volume of unused gas measured at the same temperature and pressure. So the first thing is to get our equation. We're told that carbon 2 oxide, which is CO, reacts with oxygen to produce carbon 4 oxide, that's CO2. We'll balance our equation. We have 2 oxygen plus 1 oxygen on the reactant side, making 3, and we have 2 over here. So to balance the equation, we place 2 over here, and so we have 2 oxygen, then we place 2 here. So we have 2 carbon, 2 oxygen, making 4, then 2 times 2 is 4. We have our equation balanced, and all these are gases. From the question, we are told that 100 cm cubed of CO reacts with 80 cm cubed of oxygen. We have to calculate the resulting gas and the unused gas volume at the same temperature and pressure. Now let us get our volume ratio. We have 2 volumes of CO, we have 1 volume of oxygen, and we have 2 volumes of CO2 for 1 mole of each. 1 mole of carbon 2 oxide is 50 cm cubed, and 1 mole of oxygen is 80 cm cubed. Hence, we are going to make use of that of CO2 because it is lower to get the volume of the product. So for the product, we have 2 volumes times 50, and that is 100 cm cubed. That is the volume of the resulting gas. Then we have 2 volumes of this, which is going to be 100 cm cubed. Now we have 1 volume of oxygen to be 80 cm cubed. Hence, we are going to use the lower volume, which is 50. So 80 minus 50, that gives us 30 cm cubed. So we have that volume of unused gas, which over here is oxygen, is 30 cm cubed, and volume of resulting gas, which we have it as 2 volumes of CO2, and that is equal to 100 cm cubed. And so that is the answer to the question. Alright, so we want to look at mass liquid volume calculations, still under application of the mole concept. Here is the first question, which says that what volume of 2 molar hydrochloric acid will be required to react completely with 6.5 gram of zinc? So we have zinc reacting with HCl to produce zinc chloride plus hydrogen gas. Here we need to balance our equation first, and so we have 2 hydrogen atoms here, we have 1 here. So if we put a 2 here, and ZnCl is ZnCl2, so this is zinc chloride, and this has the equation now is balanced. Our point of focus in this question, we were told that we have hydrochloric acid to react with zinc. So these are the 2 references in this particular reaction, and we were told that 6.5 gram of zinc, and then what is the volume of 2 molar of hydrochloric acid. Now from here we have 1 mole of zinc to 2 mole of hydrochloric acid. So the first thing we need to do is to get the number of moles of zinc that will react with hydrochloric acid. From what we have here, the relative atomic mass of zinc is 65. So we have that 65 gram of zinc requires 2 moles of hydrochloric acid, not 2 molar, because we're given 2 molar. 2 molar is different from 2 moles. Then 6.5 gram of zinc require how many moles of hydrochloric acid? So we have it that would equal to 2 times 6.5 over 65, and that will produce 0.2 moles. So from this question we need 0.2 moles of hydrochloric acid to react with 6.5 gram of zinc, and we're given a concentration of 2 molar of hydrochloric acid. Now we have to find the volume. Over here, this 2 molar means 2 moles in 1000 cm cubed. That is the standard. So if you have 0.2 moles, what is the volume for that? It is this volume that we are looking for. So 2 multiplies x equal to 0.2 times 1000. So x equal to 0.2 times 1000 over 2. And we will multiply this, we have 100 cm cube of hydrochloric acid. This is the volume of hydrochloric acid which will react with 6.5 gram of zinc. Here's the next question, which says that we should calculate the mass of zinc which will react completely with 500 cm cube of 0.1 molar hydrochloric acid. So the first thing is to get our equation. We have zinc which will react completely with hydrochloric acid to produce zinc chloride plus hydrogen gas. So first is to balance our equation by putting a 2 over here. Now we're told to calculate the mass of zinc. So this is our point of reference which will react completely with hydrochloric acid. So we are looking for the mass of this that will react completely with 500 cm cubed of 0.1 molar. From our mole relationship, we have 1 mole of zinc and we have 2 mole of hydrochloric acid. We will have that this 0.1 molar means 0.1 mole in 1000 cm cubed. That's what this 0.1 molar means. So how many mole are we going to have in 500 cm cubed? And so x will be 0.1 times 500 over 1000, and this will give 0.05 mole. We will now relate it with this, because we have that 2 mole requires 1 mole. So 2 moles of hydrochloric acid requires 1 mole of zinc, meaning that these 2 moles would relate the zinc to gram, and 1 mole of zinc is 65 grams. Alright, so 65 grams of zinc. So what if we have 0.05 mole? What is the mass of zinc that will be reacted with? So we have it at x times 2 equal to 0.05 multiplied by 65. So x equal to 0.05 times 65 over 2, and that will produce 1.625 gram of zinc. 1.625 gram of zinc will be made to react with 500 cm cubed of 0.1 molar hydrochloric acid. Okay, under mole concepts, we want to look at mole fraction and mole percent. This is as simple as finding the ratio between the number of moles of a particular substance over the mixture, or the total number of moles of all the substance present in the mixture. Let us take this example in order to understand it better. A mixture of 1 mole of chloroform and 3 moles of ethanol were kept in a measuring cylinder. Calculate, Roman figure 1, the mole fraction of chloroform and ethanol, and Roman figure 2, the mole percent of chloroform and ethanol. Now, from this question, we're told that we have 1 mole of chloroform and we have 3 moles of ethanol which reacted in a cylinder. What is the mole fraction of chloroform? So the first part of the question, total moles is 1 plus 3, and that is 4 moles. Hence, for chloroform, its mole fraction is 1 over 4. 1 is for chloroform over the total mole. That's the answer. And for ethanol, its mole fraction is 3 over 4. That is the mole fraction. And for number 2, we're to calculate the mole percent. So the mole percent is having 1 over 4 times 100, and that is 25% for chloroform. And then for ethanol, we have 3 over 4 times 100 over 1, and that produces 75% for ethanol. A mixture consists of 5.6 dm cubed of hydrogen, 11.2 dm cubed of carbon 2 oxide, 2.24 dm cubed of oxygen at STP. Calculate the mole fraction of the gases in the mixture. For us to solve this question, we need to relate the volumes to number of moles, and we should take note that 22.4 dm cubed of any gas at standard temperature and pressure is 1 mole of the gas. And so we are going to relate all the gases, starting with the first one, that is hydrogen. We know that 1 mole of hydrogen gas equal to 22.4 dm cubed. Hence, how many moles of hydrogen will 5.6 dm cubed be? So we have it that X equal to 5.6 divided by 22.4, and that will yield 0.25 mole. So that is the first one for hydrogen. Then we proceed to carbon 4 oxide. We are aware that 1 mole of CO2 equal to 22.4 dm cubed. Hence, 11.2 dm cubed will give what? So we have it that 11.2 over 22.4, and when we divide this, it will yield 0.5 mole. And next, for oxygen, we are aware that 1 mole of oxygen will give 22.4 dm cubed. Hence, what will 2.24 dm cubed? What will be the number of mole? So we have it that X equal to 2.24 over 22.4, and that will give 0.1 mole. Now that we have known all the number of moles of the gases, next is we would add all the gases together. So we have that total mole of the gases will be equal to 0.25 plus 0.5 plus 0.1, and that would produce 0.85 mole. Now we can now get the mole fraction, And so we start with hydrogen. Mole fraction for hydrogen is, we have 0.25 over 0.85. Then for CO2, we have 0.5 over 0.85. And then for oxygen, we have 0.5 over 0.85. So this is 0.294. That's the mole fraction. And then we have 0.588. This is the mole fraction for carbon dioxide, and 0.118. This is the mole fraction for oxygen. Here we conclude our class on mole concepts and its application.